Good morning, this is Miss Henson. Today we're going to look at exponential functions but as word problems.
Orange first lunch Graphica.
So, for word problems, to compare them first, so you know the difference between linear and exponential, we want to look at their graphs. For the graph of f of x and g of x over here, this one's f of x, this is g of x. For both graphs, as x increases, y is what? As x increases just means as you read it from left to right, just like you read a book. So for f of x, if we start on the left, what is y doing? What is your graph doing? It's going up, which means it's increasing. Same thing for g of x. If we start on the left, follow your graph, what is it doing? It's increasing. It's going up. So for both of them, as x increases, y increases. Okay, write the equation for f of x. To write the equation, first you need to know what type of function you're looking at. What type of graph is this line? Well, that's a linear graph. So what type of equation is linear? What's your basic equation? Y equals mx plus b. So we need to find m, your slope, and we need to find your y-intercept b. So your y-intercept, that's going to be where it crosses the y-axis. That happens right here at 2. So your y-intercept is 2. Go ahead and write that in here. So plus 2. And then your slope, find your next point on the line and do rise over run. Now watch your numbers on this because it's not counting by 1. It's counting by 0.5. So this goes from 2 to 3, that's 1, because the middle is 0.5. And then 3 to 4, that's 1. So we have a total of 2 here. And then your run, well, these right here, these are counting by 1. So that's just 1. So your slope is 2 over 1, which is 2. And then plug it into your equation. So your equation is y equals 2x plus 2. Okay, for g of x, what type of equation is that graph? What type of function is it? Well, that one is exponential. That's an exponential curve. So for this one, your standard form is y equals a times b to the x. A is your y-intercept, so we need to find that on here. B is your growth, so we'll find some points to find your growth. Your y-intercept, where it crosses the y-axis, is in between a line. You could estimate it, but that's not always going to give you the correct answer. So I would just wait until we make our table. Wait until you find your growth. So find some points to plug into the table. We don't have 0 because that's in between a line. But we do have 1. It's over 1 up 0.5. Remember, these lines are counting by 0.5, not 1. So 1 and 0.5. And then the next point, you have 2 and 1. And then we can grab one more just to make sure. Go over 3, up 2. Watch your table on this. Watch your y-axis. Okay, to find your multiplier, all you're going to do is divide up. So 2 divided by 1 is 2. 1 divided by 0.5, that's 2 as well. So your multiplier is 2. So I'll put that in a second. So for your y-intercept, to double check that, just divide it one more time. Your multiplier is 2, so you're going to take that 0.5 and divide by 2. 0.5 divided by 2 is 0.25. So our y-intercept is 0.25. So your whole equation, if we plug it in, we have A, that's your y-intercept, so 0.25. B is your multiplier, that was 2. And then x goes at the top. Perfect. Okay, then we want to find f of 10. When your number is in parentheses like this, normally it's f of x, so that 10 is in place of x. So all this is telling you is to plug 10 in for x. And we want to look at f of x, so we want to look for the first equation. So we have y equals 2 times 10 plus 2. That's going to give us 22. So your answer is 22. Same thing here. Your parentheses is supposed to have x. Now it has 10. So we're going to replace x in g of x with 10. So we have 0.25 times 2. But instead of x, we're going to put 10. And you just plug it straight into your calculator. And we're going to get 256. So that's that blank. So overall, which one is increasing at a faster rate? So if we look at our graph, for our graph, our linear is going up faster. It's already at 2 when it starts, where your exponential was only at 0.25. And then it goes to 4, and your exponential only goes to 1. So our linear looks like it's growing faster. But the reason we had you find C is to see what it does once it goes off the graph. What happens when it keeps going up here? Will the exponential ever be faster? And the answer is yes, if we look at the numbers we just found. F of 10, that was only 22. And f of 10 for the exponential, that ended up being 200. So eventually, your exponential will get faster. So exponential is always going to go faster than any other graph out there. It starts slow, but by the end, it's always going to be the fastest graph that we have. It's faster than anything else. So exponential is faster. So both of your graphs have a rate of change. However, for your rate of change of f of x, for your linear, that's going to stay constant. One second.
Blue, first lunch, grab and go to the cafeteria.
So that one stays constant. That one's always going to go up 2 over 1. It's always going to be the same. For the g of x, for the exponential, that's always going to vary. That means your slope, a rise over run, is always going to be different. Like we had the 0.21 and 3.2. So for the first one, it goes up 1 over 1, but then it goes up 2 over 1. If we were to find the next point, it would go up 4 over 1. So it's going to change every single time. Your slope is not, your rise over run is not going to be the same on exponential. On linear, it will be. So find the dashed line on the graph, this one right here. What is the average rate of change? That just means slope for g of x between those 2 points. So between 1 and 4. So this is 1 and 0.5. And this is 4 and 4. How do you find slope? We can do your slope formula, or you can do rise over run. I think I'm going to do slope formula. So you have your slope formula. Remember y2 minus y1 over x2 minus x1. We did that last semester. And then we just plug them in. So we have 1 and 0.5 and 4 and 4. We can label those x1, y1, x2, y2, and plug them in. So y2 minus y1 over x2 minus x1. And then we just plug it into our calculator. You can plug it in as a fraction. Just hit enter. It'll simplify it all for you, and you'll get 7 over 6 once it simplifies. So that's your average rate of change, your slope between those 2 points on the exponential. Now, your average rate of change on exponential is not your multiplier. That will never be the multiplier. That's completely different. The average rate of change is just rise over run. The multiplier is the growth or decay factor, what it's multiplying by. So those are not the same thing. That's what this question right here is. The multiplier and the average rate of change are not the same, ever. The multiplier is how much it grows or decays. That's what it's multiplying by. And the average rate of change is your slope, just between 2 points, not of the whole graph. Okay? So, like I said, we're going to work with exponential word problems today. So you have a couple words you want to look for when we're doing exponential word problems. For growth, you're going to look for words like increasing, appreciation. That's just another way to say it's going up, it's increasing. Compounding. And then multiplying words like doubles, triples, quadruples, quintuples, all of that stuff. That just means times 2, times 3, times 4, etc. There's a lot of words that could be on that list. For decay, you're going to look for the opposite. So you're going to look for decreasing. Opposite of appreciation is depreciation. Then you got losing value. And then multiplication words here, like taking a half or a third, a 1/4, 1/5, 1/6, any of those fraction words. So taking a half, a third, a fourth, anything like that. These are the words that are going to tell you if your problem is growth or decay. So let's look at number 1. So your parents offer to pay you to study for your algebra test. They say they'll give you $5 for the first hour that you study, and then they'll double the amount for every additional hour. So what 2 things is this question talking about? What 2 values do we have? Well, we have $5. We also have the first hour, every additional hour. So we're talking about hours and money. Which one of those is X? Your time is always going to be your independent. And your independent is X. So time goes here. So X is going to be your number of hours. That's how long you spend studying. Your Y is going to be your money. Money always depends on something. Whether you're earning it, you're spending it, whatever you're doing with money, it depends on you doing something. So that's always going to be Y. So this is the amount that you're paid. Total amount that you get paid. Okay, what's the initial? Just for you to start studying, what are your parents going to give you? Well, they're going to give you $5 just for you to start. You're going to get $5. What's the multiplier? What is your money going to change by every single time? How much is it going up or down? For that, you want to look for your exponential growth and decay words. Which one of these words in this chart do you see in your problem? Right, doubles. They're doubling the amount every additional hour. So doubles, that just means you're multiplying by 2. So your multiplier is 2. So now you have your initial, you have your multiplier. Now we can write our equation. So remember, y equals a times b to the x. A is going to be your y-intercept, your initial, and b is going to be your multiplier, which is growth or decay. In this case, growth. So for your equation, y equals, what's your initial, your y-intercept? That was 5. And then your growth or decay, your multiplier, that was 2. And then x always goes at the top. Does this situation represent exponential growth or exponential decay? Remember, for growth, your multiplier has to be greater than 1. For decay, your multiplier has to be between 0 and 1. Not less than 1. There's no such thing as a negative multiplier. It has to be between 0 and 1. So which one does 2 fall under? Is it greater than 1 or between 0 and 1? Right, it's greater than 1. So this is a growth. The amount of money you earn grows every hour. So how much will you be paid if you study for 4 hours? So what could we do with 4? Would we plug that into x or would we plug that into y? Correct. This is hours. Hours was our x variable. So we're going to plug it into x. So y equals 5 times 2 to the 4th for 4 hours. And you can plug this in. Let me get rid of that. So 5 times 2, and do the little rooftop up arrow and put in 4 hours. And we're going to get 80. Now remember, for word problems, we have to use correct unit. So this is not just 80. What is y? This is y equals, y was the total amount paid. So this is $80. So $80 is your correct answer. How many hours would you need to study to make more than $1,000? $1,000 is what? X or Y? Right, the amount you get paid is Y. So that would be plugged into Y. The weird thing about exponential equations is when your x is in the exponent, you don't know how to solve that yet. You don't know how to get rid of it. You're going to learn it in a future class, but not in algebra. So how we're going to solve this is not actually plugging it into the equation. We're going to plug it into the calculator and look at the table. So just go to y equals, plug in your equation. 5 times 2, do the little rooftop, and put in x. So that's your equation. And we're going to look at our table. So hit second graph. Now the question says, how many hours would you need to study to make more than $1,000? We already said $1,000 is your y value. So go to the y side of your table and figure out where it hits more than 1,000. It's not going to hit exactly 1,000. That's why it says more than. So where does it go above $1,000? So just scroll down till you find over 1,000. So right there, 1,280. That's hour 8. So that's where it's over $1,000. That's going to be our answer. In 8 hours, you're going to have more than $1,000. Just look at your table. Okay, let's try example 2. Okay, example 2. The given rate is a fraction or a percentage. And that's going to have the question of how many are there now. So they're going to give you a certain value and then ask you how many are there now. So a computer virus is affecting the technology center in such a way that each day a third of the virus-free computers is infected. The number of virus-free computers is recorded in the table below. So this table right here. So what are our variables? So we have your table right here. We have days and we have virus-free computers. Which one of those is X? Well, X is going to be your time, so your days. Okay, and then your Y, that's going to be your virus-free computers. I like to call this the uninfected computers because we already have computers in our problem that are infected. So that we know the difference between them, I'm going to call it uninfected instead of virus-free. It's the same thing. I just think it makes more sense to put uninfected so that you can definitely tell the difference between these two. If you put virus-free computers, that is completely fine. Your answer is still 100% correct. So, how many computers are in the technology center? This is just asking for your initial. How many do we start with? Whether they're infected or uninfected, how many are there? Well, that's going to be at 0. At day 0, we had 27 computers that were uninfected because the virus hadn't started yet. So we have 27 computers in the technology center. Write the equation that represents the virus-free computers. This is where this question up here comes into play. How many are there now? The word problem said a third of the computers are infected every day. So we have a third of the computers infected. Our question says how many of them are virus-free, meaning how many are uninfected. So this 1/3, this is not your multiplier. This is not what you're going to plug in to your equation. This is not the multiplier because that's the infected computers. The equation has to be virus-free computers. For that, we want to go to our table. Go to your virus-free computers. And just like the lesson a couple days ago, we're going to divide up. So 12 divided by 18, just plug it into your calculator, and you're going to get 2/3. Double check it, 18 divided by 27, plug it into your calculator, and again you're going to get 2/3. Now this is not, when you plug it into the calculator, 18 divided by 27, you're going to get 0.6 forever. You cannot put that in an equation. You can't use repeating decimals. So you just have to hit math, enter, enter to get that 2/3. That's all you have to do. 2/3 is the amount of uninfected computers. Now, why are those different? Why did they give us 1/3 when the answer is 2/3? And how do we get those from each other? Well, if you're talking about fractions here, you're looking at a third of them are getting infected every day. So if we split this up into 3 parts, This third right here, this is your infected.
Orange, second lunch, grab and go, cafeteria.
So then what's left over? If a third of them are infected, how many are not? Well, these two right here. These are not infected. That gives you 1/3 right here and 1/3 right here for a total of 2/3. So that's where this 2/3 is coming from. That's why they're different. 1/3 is infected, which leaves 2/3 uninfected. That's why these are different. It just depends on what the question asks for. If the question asks for uninfected computers, we use 2/3. If the equation had asked for infected computers, we would have used 1/3. Just watch your equation question. Watch what it asks for. It's very specific. So for our equation, again, you have y equals a times b to the x. A is your initial, your y-intercept, and b is your multiplier. So what's your initial? Your initial was 27 computers. And what's your multiplier for the virus-free computers? The uninfected. That's 2/3. That's the one we're going to use. So 2/3, and then as always, x is going to go at the top. So how many days before all the computers are infected? So basically, when are you going to have 0 computers? So 0 virus-free computers. So we can go back to our variables. Which one is the computers? Well, that's y. Just like I said on the other problem, if we have to plug into y, we cannot solve this. We cannot get rid of this x right here. There's no way to do it. So if you have to solve for x, you cannot do it like this. You have to look at your table. So we're going to go to our table, go to y equals, plug in your equation. I'm going to do this as a fraction. Now I'm going to plug it in as divided by 2 divided by 3 so that I can get decimal answers. And you'll see why in just a second. So instead of a fraction 2/3, put 2 divided by 3. So that when you go to your table, you can see the decimals instead of the fractions. So we want to find out when there's going to be 0 virus-free computers. So when will y reach 0? So if we scroll down, when does it hit 0? We still have decimals. And then we get to these E numbers. These E numbers are not 0. They're not actually negative. This just means the decimal was way too big and they can't plug it in. They can't actually show you the decimal. The thing about exponential equations, I'll zoom this out just a little bit. When you're looking at the graph, it's going to get closer and closer and closer to 0, but it has that asymptote right here. If you remember from last week, that asymptote means it's going to get closer to this line, but it's never actually going to hit it or cross it, which means this is never going to hit 0. So how do we answer this question? Well, in that case, you just want to look at your table and figure out where it's less than 1. Because if you have less than 1 computer infected, that means there's no computers, less than 1 computer uninfected, that means there's no computers infected. So to solve this, we're going to find out where it's less than 1. because it's never going to hit 0. So go to your table, scroll down until your decimal is less than 1. So if we scroll down, that's going to happen at 9. That 0.7, you can't have 0.7 of a computer infected. It's got to be the whole computer or nothing. So if any of it's infected, it's all going to be 0. That means 0 computers are left. Some part of that computer is infected, 0.7 of it is, so there's no virus-free computer left. That's where it hits 0. So that's going to be at 9. So 9 days. So because this is never going to hit 0 because of that asymptote, you just have to figure out where it's less than 1. That's all you need to see. You're going to have a couple of those. So all you have to figure out is where it's less than 1. Okay, example 3. What if there were intervals of time? So where it's not just changing every month or every year, it's changing a specific amount of time. So for this one, suppose 15 squirrels are taken to an island and then their population triples every 8 months. How many squirrels are there left in year 4? This is what I'm talking about. This doesn't just say, oh, it triples every year or it triples every month. This is a very specific amount of time. For these, our variables also have to be that specific amount of time. So when we do our variables, for x, we're going to use 8 months, not just months. This is going to be the number of 8-month intervals, because it's changing every 8 months, not every month. Like on the last problem where it said each day, so we made x days. This is very specific that it's 8 months, so we have to be specific and use 8 months. And what's happening every 8 months? What's changing? The squirrels, their population's tripling. So our squirrels are changing every month. So this is our total squirrels every 8 months. Okay, so what's our initial value? How many are we starting off with? Well, we're starting off with 15 squirrels. And then what's the growth factor? Go back to our table on the front page, and which one of those words in this chart do we see in the problem? We have triples. It triples every 8 months. Triples just means it multiplies by 3. So our growth factor is 3. So then write your equation. So y equals, remember it's y equals a times b to the x. A is your initial, so we'll put 15 first. B is your multiplier, so that's our growth here. And then x at the top. Okay, use your equation to answer the questions with correct units. So the question says, how many squirrels will there be in 4 years? So what do we plug our time into? Well, time is x, so we're going to plug it into x. And these we can solve. You can look at the table if you want to, or you can just plug into x. However, we're not plugging in 4. Why? The question says how many will there be in 4 years? How often is it changing? How often does it triple? It triples every 8 months. That's why we made our x value 8-month intervals. So we can't plug in 4 because it's not changing every year. It's changing every 8 months. So we need to change years to months. How many months are there in 1 year? 12. Right. So in 4 years, how many months are there? All we have to do is multiply that by 4, and we'll get 48 months. Now, that's not the number we're going to plug into our equation either, because it's not changing every month. How often is it changing?
Blue, second lunch, grab and go to the cafeteria.
It's changing every 8 months. So because it's changing every 8 months, we're going to divide this by our 8-month intervals to see how many times it actually changes. So 48 months divided by 8 months is going to give us 6 changes, 6 intervals. That's what we're going to plug in to X. So we're going to plug in 6. So change your years to months and then split it up among those intervals. We have 8-month intervals, so we just divide by 8 and we get 6. And then we just plug it in. So we got 15 times 3. Put your exponent as 6. And we have 10,935. So in 4 years, with it changing every 8 months, we're going to have 10,935. What's your correct units? Squirrels. That's it. Okay, so try the rest of the examples. They're all based off of these. Watch your time. Watch if there's any intervals. And watch your equations. Like this one, it asked for uninfected computers. The word problem gave us the infected, the 1/3 infected, so we had to go to the table. So watch that. Make sure you know what it's asking for. Good luck.